Okay, now we go to another operation which is called pointing. Now, pointing is basically, we are just taking, a structure and, we point to one of the elements just to make it as a special, right? A good example is that, given a tree, let's say, like just take any tree, right? And then you say that, okay, one of the vertices I want to make special, right? I will make it special, right? I'll just say that this vertex is now special. Or I'm just pointing to this vertex saying that, okay, this guy is the main guy, right? So, this, what is this? This is precisely a rooted tree, right? A rooted tree is a tree with a one vertex which is marked as special or pointed by, something saying that this is the root. So, the pointing of the species of trees must make a species of rooted trees. So what is pointing in the picture? So you have this set, right? And on this set you are selecting one of the elements and saying that that guy is special, right? That is it, right? So you are making it as a special vertex, and you get a router structure. But what is this? We can check or we can select any of the elements as your element to be pointed, right? You can point to any of the elements, which means that there is a one-to-one correspondence between the structures on f dash f not dash, basically f point, right? F dot of u and f of u cross u, right? The Cartesian product of f of u, right? The set of all f structures on the set u with the set u itself, because for each element I can say that, okay, that element is special, right? First element of u, second element of u, third element of u, each one can be associated with this, say that this is the special element. So basically there is a bijection to this f of u cross u, right? The Cartesian product. And from this, it is immediately clear that the cardinality of f dot on an element set, f dot of n, is actually n times f of n, right? Because whenever you have a structure, you have n possible ways to point it, right? It's any of the n elements of u can be marked as special. And if this is true, of course, f dot of x must satisfy the following identity, right? It must have the form that like summation n into fn, because that is the number of elements on an n element set, x raised to n by n factorial. Now, what is this? Which is basically, if you take one x outside, you will get it is basically as x times d by dx of f of x, right? Because f of x is fn x raised to n by n factorial. You take the derivative, multiply with an x, you will get this form. So therefore, it is basically x into d by dx of f. But d by dx of f of x is the generating function for f dash of x, right? And x is the generating function for the species of singletons. So therefore, you can see it as the product of the singleton species and the derivative species of f. So f dot of x is basically x dot f dash of x. And here is a pictorial representation. You want to see that f structure on the set u, where one element is marked special, is basically identical to, right? You take the element that you want to make it as special outside, okay? Then you replace that element with a new element star, put an f structure on this, right? Now forget about this particular element, right? And just replace it with this element, right? And then you will get the f structure on this, right? Or basically the f dash structure on the set minus this element, where this element is now marked special. Therefore, you will get this as a pointed structure. Now we conclude this lecture with a very nice application to count the number of labeled trees, and this was given by Andre Joel. And we already counted the number of labeled trees in our course earlier using some techniques, and then we showed that it's actually n raised to n minus 2. So we are going to prove the same thing, but now using the species. Okay. So we have A as the species of trees. Okay, species of trees. A is the species of trees. Then what we do is that we take the species of trees and apply pointing once. So once we apply pointing to species of trees, we will get the species of rooted trees, right? We already saw that if you take a tree and point to one element, you will get a rooted tree, right? So the tree A, right, becomes a rooted tree, right? So whatever tree you start with, you mark any one of the elements as root, and you get a rooted tree, right? So therefore, from the species A, you will get the species capital A, right? When I take the pointing operation, so A dot. What happens when you do the pointing once? When you point it once, if you had whatever, like some number of elements in here, suppose you had you are looking at an n vertex tree here, then you have n different ways of pointing here, right? So from each tree you can make n new different trees. So whatever was the number here, it will be multiplied by n, right? So you will get n times as many trees when I do this pointing. We will keep track of this, right? So we have started with some number of trees. Then we say that whenever you start with an n vertex tree, after the pointing you get n times that many trees, right? Rooted trees. Then you point again, right? So where we are allowed to repeat, only point to the same vertex if you want, right? You are allowed to point the same vertex again, but so we don't lose on any choice, right? So we can point again to any of this. So you mark, it's also as a second point, right? So we get doubly pointed trees, right? So you get a rooted tree where you point once more. And this new structure is called a vertebrate. So what is a vertebrate? A vertebrate is an animal with a spine. Okay. Right. So we call the species of vertebrates. So what is it in our case? So we have a tree where we have two vertices marked as special. Okay. So the first you pointed to some element, then you pointed to an element, and the first element is called the tail, and the second element is called the head. Now, of course, this can be the same because we allow repetition. So in that case, it happens to have the same tail and head. In this case, it is called a degenerative, vertebrate. But otherwise, it is non-degenerative vertebrate. So it doesn't matter. We will look at all possible vertebrates. So we look at vertebrates with one tail. The first pointing is giving you the tail, and then the second pointing gives you the head. Now, once you have a tail and head, there is, so since we are looking at trees, there is precisely one path starting from the tail to the head, right? So there is a unique way, a unique path defined on trees between any two vertices. So in particular, you have a unique path between the tail and head. Now this unique path says what? It says that I start from you, then go in this particular direction, fixed direction, and going to the head, which says that it is basically a linear order on these vertices that we are along the path. But now each vertex on the path can be thought of as a special vertex, right? It can be thought of as a special because it is part of the path itself. So I can think of this vertex and this part, whatever remains here is a rooted tree because it is a root. Then this vertex together with whatever is here could be empty, only just this vertex alone, right, is another rooted tree on one vertex. Here is a rooted tree on this, right? Here is a rooted tree here, just one vertex. Then here is another rooted tree, right? So you can think of these vertices on the path as a rooted tree, and you are putting a linear order on this, right? You are saying that you have to go in this particular order. So it's basically a linear order on rooted trees, right? So vertebrate is basically a linear order on rooted trees. But the linear order is on a non-empty set of rooted trees, because if the set is empty, then we cannot talk about this. So therefore, we have a linear order of non-empty set of rooted trees. So we are looking at L plus of A, where L plus is the species of non-empty rooted trees, right? So V is actually equal to L plus of A, right? Okay. Now, we know that the species of linear orders and the species of permutations has the same number of elements, right? When you look at the exponential generative function, they are the same. So therefore, it counts the number of linear orders on a set and number of permutations on a set are the same, right? It's basically n factorial, where n is the cardinality of the set U, right? So therefore, they have the same generating function, which means that they are called equinumerous. They have the same number, even though they are not the same. There is a one-to-one mapping, right, between them. So therefore, they have the same number. There is a bijection. Therefore, there is the same number of elements. So they are equinumerous. And because of this, if I substitute L plus of A, right, it has the same generating function. So you are substituting A on the same generating function, L plus of A, and S plus of A has the same same cardinality, right? The species L plus of A, right, and the species S plus of A must have the same number of elements on a set U. Okay, in fact, I should write it as not just this, but this together with some set U, right? Some set U on U, or on N, whatever, right? On an n element set or on a set U, then they are the same, right? The cardinality is the same. Now, if you recall, right, when we are looking at this graph, we proved that the permutation of rooted trees is basically endo functions, right? Because endo functions can be thought of as like if you look at the map of endo function, we saw that like it basically has this nice structure, right? All the paths on the trees go to a specified vertex, and all these vertices, the end vertices of the trees, right, the roots of the trees, sitting in a cyclic structure, right? So therefore, endo functions are basically a permutation of rooted trees, right? Therefore, S of A equal to n, right? Because it's basically we proved this in an earlier part of the course also. I mean, in the same lecture also, right? I think, yeah. So therefore, S of A is equal to n, right? En. Therefore, S plus A of A is, S plus of A is equal to n plus, because, look at the non-empty structures, right? If you have at least one element, we can talk about this. So therefore, for n greater than or equal to 1, cardinality of END of n, we know, is equal to n raised to n, right? For any n greater than or equal to 1. And therefore, because of this identity, we get that cardinality of S plus of A is equal to n raised to n for n greater than or equal to 1. But then we know that these two are equinumerous. So therefore, the cardinality of L plus of A is also equal to n raised to n for n greater than or equal to 1. But how did we get this L plus of A? L plus of A we got, this is basically, is a number of vertebrates, right? It is basically the species of vertebrates. But the vertebrate is basically a doubly pointed tree, right? So a tree on n vertex pointed twice. So if it is pointed twice, we know that the number multiplies by n into n, right? N square. So you have n square times whatever was the number of trees on an n element set, right? So A of n. Therefore, cardinality of A of n must be equal to right? N raised to n divided by n square, which is n raised to n minus 2. So this shows that the number of trees is precisely n raised to n minus 2. So this is another way to prove the number of labeled trees, right? Count the number of labeled trees. And we wind up with a couple of homework questions. And the first is to show that the vertebrate species can be also thought of as the species A, right, of fruited trees plus V dot A. Okay. Now, once you prove this, so to prove this, I give a hint. The hint is that the vertebrate is, as I mentioned before, is said to be degenerate if the head and tail is the same, right? Otherwise, it is non-degenerate. Now, to prove this, you can take the vertebrate and then look at if it is a degenerate one or not. If it is not degenerate, then you can cut off the tail, right? Cut off the tail and then look at the remaining, and then use this as a hint to prove this, right? Then deduce the following, that for n greater than equal to 1, n power n is actually equal to summation k equal to 0 to n minus 1, n choose k into k raised to k into n minus k whole raised to n minus k minus 1. A third question is to show that the pointed species of the product of f and g, f dot g dot, is the product of the pointed species f dot and g plus f dot g f times g dot, right? So f dot times g plus f times g dot. Similarly, show that f composition g dot, this is, I will write it more clearly, f composition g dot is actually equal to f dash composition g times g dot. Okay. Now, prove that f composition x, right? X is the species of singleton, is actually equal to x composition f, which is actually equal to f itself. So therefore, for composition, x is a unit. Okay, I think that's it. So we wind up the short introduction to the species of combinatorial structures, and if you want anything further on this topic, you can look at this book, which is a nice book, Combinatorial Species and Tree-like Structures, by the following people: Bergeron, Lebel, and Leroy. Okay. So if you want, you can refer to this, where there is more details on this, with lots of exercises and also much more advanced topics. Okay, so I will wind up with this for today. See you in the next